welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about old ideas. Nothing new here.
Correct.
We're going to talk about specifically the difference between scalars versus vectors. So, Mr. Sadler, scalars have magnitude. What does that mean?
Most people know the magnitude of an earthquake is just that number.
Yeah.
It's nothing special. It's just the amount.
Just a number. Oh, I like that. Amount. Write that down. Amount.
Where?
Vectors have what?
A direction.
They have magnitude with direction.
So if I say I'm going to Grandma's house at 30 miles an hour, that's a scalar. And if I say that it's east, that's a vector.
Right. So you've got to assign where or what direction the force or the velocity or the acceleration is. So these are numbers with direction. A scalar can only be positive. A vector can be positive or negative. And so specifically, we're going to talk about scalars and vectors from a Chapter 1 standpoint when we described motion. And so, per your book, and your investigation that you just did, we talked about things like distance versus displacement.
Right. So if I go 30 miles to Grandmother's house and come back, the distance is 30 miles, but the displacement is 0.
Right. So the displacement idea is from start to finish, and you measure that distance. So this could be the beginning, this could be the end. You could take any old path
To get there.
but the displacement is just start to finish. If we were to measure out the length of this entire line, okay, distance is total, all of everything that you did there. Okay.
Correct.
From a scalar perspective, we talk about speed, which we have calculated speed over and over again in many
Right.
ways, from momentum to energy to Chapter 1 concepts of using our DT and our VT graphs, etc. Speed is just, we've talked about it, 30 miles per hour.
Correct.
Where vector would be velocity, and so now we have to go speed
And a direction.
with direction. And I think maybe we mentioned this before. This is your car's speedometer. This is your car's GPS. So the GPS will always tell you what direction you're driving and how fast you're going. I'm always amazed as to how accurate that is. The GPS is communicating with the satellite up in space, and my position is being triangulated, blah, blah, blah. But it's pretty accurate, pretty within 2 or 3 miles of my actual speedometer.
They actually build in a factor into that so that terrorists can't use it. They build in an error factor that the military uses.
Really?
Yeah.
I didn't know that.
So yours isn't as accurate as a military one where they can pinpoint,
Exactly.
a postage stamp.
Okay. And then the last vector that we're going to talk, so we talked about displacement and velocity. The last vector is acceleration. Now, there is no scalar equivalent. And we know that acceleration can be positive or negative, and we spent a lot of time, if you recall, if we have, how did we do this before? If we have a positive velocity with a positive acceleration, we talked about the resulting motion. So yeah, V, A, and then the motion, remember?
Mm-hmm.
So if we identified that if both velocity and acceleration were the same, that the object was speeding up.
Correct.
And we note right here, I said velocity, I said acceleration, they can be positive or negative. If they're opposite of each other, then the object has to be slowing down.
Correct.
And, we can talk about some of these things. If you have, we should probably put initial velocity. If this is 0, then we can work through this as well. But we work our way through this. This is also speeding up.
So like a positive velocity, so I'm going 30 miles an hour, and a negative acceleration slowing down, so I would be slowing down or stopping. A negative acceleration backing up, speeding up, positive velocity slowing down.
And then if you had some positive or negative velocity, zero acceleration, of course, that's constant speed or constant velocity. See, even I mess up on that terminology. So we've got to know we're talking about vectors. And why are we doing this? Why are we rehashing this conversation about speed, velocity, acceleration, etc.? Well, it all applies to roller coasters. So I haven't been to too many theme parks. Been to Great America quite a few times. I love the Raging Bull. And I think it's probably the best steel roller coaster that they have at the park in terms of its speed and its rates of acceleration and the drops and things like that. So you come up off of this huge hill, and it seems like almost a straight drop, and you actually go under the ground, and you shoot back out, and I believe you go immediately into a loop. And I don't think the loop is quite that tight. But what's interesting about this is we talk about this from a physics point of view. Redraw that loop there.
So we're going to talk about gravitational potential energy or kinetic potential energy?
Right. So, I mean, we're going to get into the energy and the force side of this in another pod. But as we're going through the loop here, our speed is pretty much constant. Doesn't really change a whole lot. But we get that thrill effect where people are screaming because we are accelerating. So my question goes to you, Mr. Sadler. If the speed is constant, how in the world are we accelerating?
Because it's centripetal acceleration, like turning a corner in a car.
Right, so our direction is constantly changing. So at this moment in time, we're going this way, and then we're going in all of these different directions, and it's changing. The direction change is very quick, and as a result, we are experiencing, yes, that centripetal force, or that F sub c, all right, is causing the centripetal acceleration, and so all of this goes to a constant change of direction.
If you like the constant change of direction, you should be going on the Ragin' Cajun that keeps whipping you around the corners.
Ragin' Cajun?
Yeah, it's like a little teacup thing that goes around.
You lost me with teacups.
Yeah,
yeah.
Exactly.
So I say, we talk about this in class a little bit. All right, roller coasters versus carnival rides. Now, they both give you that thrill, and they both make you want to throw up sometimes, and they make your stomach, your stomach becomes confused about its location. Okay, here we're talking about high rates of velocity, you have big distances to travel, etc. And so we also have changes in velocity, so we have accelerations. We don't have big velocities because of safety features. We don't have big distances because of size restrictions. But we do have changes in velocity that lead to accelerations. So the carnival ride is all about going in a circle.
Tilt-a-whirl.
The tilt-a-whirl, yeah, that's like the teacups, except on the teacups you have some controls. You get to spin at least the cart you're in.
Right.
On the tilt-a-whirl, I just think you're at the mercy of the operator, if I recall correctly.
Right. Well, it has a little incline that spins you around.
Right.
You can lean a little bit, but
a little bit.
Yeah.
So I avoid carnival rides. I like acceleration. I don't like the constant change in direction.
Well, the other thing about carnival rides is they travel around the country and they don't have the same safety records as some of the big theme parks.
When you take something apart every weekend and put it back together on Wednesday night, there's a decent chance you might lose a part or that you'll have extra parts when you're done.
Right.
And if you've ever had to take your car apart and put your car back together, if you have extra parts at the end,
it's not good.
That's not a good thing. And I imagine that happens on occasion at the carnivals. The beauty of the roller coaster is it's always It's always together. Once you put it together the first time.
But if you like to live dangerously, carnival rides is the way to go.
Oh, absolutely. So, because I don't like to throw up, I avoid the carnival rides. But we still have accelerations due to large change in velocities. This is due to a directional change, okay, whereas this is due to a speed, I'm sorry, I said it again. No, actually, we can say it, a speed change, because we're changing just the number as we zip down the hill. Okay, so I believe that covers why we're talking about velocity, acceleration versus speed again. So signing off, this is Mr. White.
And Mr. Sadler.